All right, so thank you for joining me today. We're going to look at some ideas involving angles and polygons. So what I have in front of us here are three figures, two triangles and one quadrilateral. There's my two triangles. These triangles are not necessarily drawn in any particular fashion. I do want to kind of point out here that this one, although it might look like a right triangle, is not a right triangle. We can actually turn it that way. You can actually see it a little bit more clearly that it definitely is not a right triangle. And I'm pointing this out in particular because especially if you're teaching small children about math, really any students for that matter, perspective is a huge important aspect of what you're seeing. I was actually working with some elementary teachers many years ago, and this particular school, particular spot, they were having a lot of problems with their students not identifying parallel lines properly. In fact, the only way they could do it is if the parallel lines were actually set up so that they were at an angle. So they would actually set the two parallel lines up side by side running like this, and the students were saying, oh no, those lines aren't parallel. They have to be parallel when they look like that. So not only were they staying the same distance apart, but they also had to be going in the same direction. I'm just bringing that up because it's important sometimes to make sure that you see things from different perspectives, okay? For instance, when you first look at this quadrilateral, you might have thought, well, that's a trapezoid because the top and the bottom are parallel or something like that. And if you move it around, you can very clearly see that they're not. You say, well, this other triangle, this one might be a right triangle. Very well might be. We can test that in a number of different ways. One of those is to get out our protractor and line up the center of my protractor right there with the corner of the figure, and sure enough, it is actually a right triangle. Now the other thing is that this is not exactly a straight line. That's because I'm not very good at cutting shapes. So you'll have to pretend with me. All right. So what does all this mean for us then? What can we do with this stuff? Well, the first thing I want to do is I want to move these off to the side, and I just want to talk about this one right here for a second. And what I'm going to do is I'm just going to come down here, use my straight edge. I'm just going to draw a line like that. I'm just going to put a point right there just for reference, not really doing anything other than that, just putting a reference. Now the idea is that this is a single line, and the measure from here over to here is 180 degrees. So we have a line. I can label this as A, I can label this as B. So we can say, and we can call this C if you want to, angle ACB is 180 degrees. This is not a straight angle. That's not really a thing. A lot of people try to make it a thing, but it's not. It's not a straight angle. This is an angle of 180 degrees, also known as a line segment. So if you're going to label that, that's fine. Do it that way. Now, what I'm going to do here is I'm going to label these triangles. Here's 1, 2, and a 3. And again, this is pretty standard notation when you want to label the inside angles like that. If I were labeling the points, I could label it as A, B, and C, or D, E, and F, whatever. But I'm dealing with the interior there, so I'm going to label it 1, 2, and 3, just to make it a little bit easier to talk about. And what I'm going to do is I'm going to physically tear off each angle. Okay, so I'm just going to tear it off as neatly as I can, just like this. And when I do that, I'm going to put that so that all three of them match up right here at that spot. And when I do that, you can see that all three of those work out to give us 180 degrees. And what we've just demonstrated is a physical way that we can show that three angles of a triangle, the three interior angles of a triangle, sum to 180 degrees, which is pretty cool, I think. So there's that one triangle that was just drawn. It wasn't necessarily anything special about it. It was just an obtuse triangle because one angle was greater than 180 degrees and the other two were acute angles because they were less than 90 degrees. Here's my next one. We'll go ahead and label this as 4, 5, and 6 so we don't mix up any of our angles with the previous one. And once again, this one's a little bigger, so it'll make the tearing process a little bit easier. I'm just going to tear those those angles off. I'm going to tear apart my triangle. I always thought it was kind of fun to tear. Let me rearrange those, and once again, they add to 180 degrees. We can do this over and over again. So if you're actually in a classroom full of small children, and the videos I'm making right now is actually kind of geared towards people who are going to elementary education, but this does apply to anybody. You can do this with any triangle. Redraw any triangle, cut it out with scissors, nice and straight, straighter than mine are. And what you'll find is every single time those three angles will sum to 180 degrees. You can place them down like that and you can prove it very easily. It's a lot easier than getting your protractor out and measuring each individual angle. You can just tear them and rearrange them, and there you go, right? So that's pretty nice. Now what about this one though? Has one more angle to it. Instead of a triangle, it's a trapezoid because we have, not a trapezoid, I'm sorry, a quadrilateral. We have 1, 2, 3, 4 sides. Nothing in particularly special about this one. None of the sides are parallel. None of the sides are meant to be congruent. You can actually tell the top and the bottom are definitely not congruent. Keep in mind that if I were to turn it this way, I'd be talking about the left and right hand side of it are not congruent. And also, when you turn it sideways, you can more or less see that this side, this piece, this edge right here, and this edge are also not congruent. So none of the sides of this triangle are congruent. And just point of clarity on some vocabulary I'm using here. The sides of this quadrilateral, I have 4 of them, 1, 2, 3, 4. These are 4 edges. Edges is a more generalized term. Side is a specialized term. A side is a straight edge. Okay, so point of clarity there. Now, I've already done 6. I'm going to label these as 7, 8, 9, and 10. Okay. Now, when we do this one of the things that's kind of weird is like we added one more angle. So we add 90 more degrees. That would make sense, right? We're just adding a little bit more. But let's see what happens. And I'm physically going to tear these. Now, this is another piece of this before I tear. I could also think about this being, if I draw either of these two diagonals, okay, from either spot, I could draw from this upper corner to this lower corner. I could draw from this vertex to this vertex, which is mathematical terminology for those corners, is the vertexes. I can draw from opposite vertexes, either set, doesn't matter. I just draw one diagonal from opposite vertexes, and I create 2 triangles. And we already know the sum of those angles for those 2 triangles is 180 degrees. So if I have a triangle and another triangle, then that gives me 180 degrees in this interior triangle and 180 degrees in this interior triangle, which means that the 4 of them has to be 360. That really is bothersome to some people. So let's just do this the same way we did the other one. Okay, I'm going to tear out these corners again, and we're going to see what happens, right? Now, we've already talked about it being a triangle, right? So let's just see what happens. And put those, match those up as best I can. There's that one. Some of you are thinking, oh, this isn't going to work. There's no way this is going to work. We got too much ground to cover. Some of you may have even been a little nervous about it. It's like, oh, no, oh, no. Oh, look at that. I find this to be amazing. It's just simply amazing because all 4 of those worked out to be 180 degrees. So when we had 3 sides, let's say n is the number of sides. We had 3 sides. We had 180 degrees for the interior angle. So this is the number of sides, and this is the interior angle sum. Okay, the interior angle sum is 180 degrees. N was equal to 4. This was equal to 360. So what about if we had 5 sides, right? Or 6 sides, or 7 sides? What would those work out to be? Well, again, you can get some piece of paper and just start measuring this out. Now, with 5 sides, what you might need to do is rearrange it a few times to get it to fit, but it's still, you can still work it this way. You're still going to be able to do it this same idea. There's another way to look at this as well, and I want to point that out. Is there's an alternate way to look at this, 2 different ways to look at this once you get past this point. And I want to kind of bring that up here in a second. But that's the beginning of this, right? So what's the next one? Do we add 90? Did we double? Did we add 180? Well, we definitely didn't add 90, so it's 180. So did we double it, or did we add 180 every time? So is the next one 720, or is the next one 540? That's a very big question that we need to answer, right? So let's think this from another direction, right? We got a triangle, and 1, 2, and 3. The sum of those gave us 180 degrees, right? So this gave us 180. We did some arbitrary quadrilateral in 1, 2, 3, and 4 in this instance. That gave us 360, right? Now, if we do some type of pentagon, doesn't matter, some arbitrary pentagon there. This is angles 1, 2, 3, 4, and 5. And I'm reusing 1, 2, 3, and 4, and 5 just to emphasize the fact that this has 5 sides, which means it has 5 angles. Also keep in mind that with these shapes that we're dealing here, these are convex polygons. They're not necessarily regular polygons. A regular polygon means that all the sides and angles are equal, but they do have to be convex. As soon as we get outside the realm of convex, it changes the relationship a little bit here. But these have to be convex polygons, and they have to be, by definition, they have to be closed to be a polygon. But the question is, how many angles are there? And there's 2 different ways we can look at this one, right? So first way, I'm going to draw this one way and then we'll draw it another way. First one is I'm going to pick one of these vertexes. Let's just say 1. And when I do that, I can draw a diagonal there and a diagonal there. Now I have 1, 2, 3 triangles. This one had 180 degrees. This one had 180 degrees. This one has 180 degrees. So that gives us 540. Now, another way to look at this. Again, my arbitrarily drawn pentagon, right? This time, what if I kind of pick a center point, if you will? It's not a circle, so it's not a true center point, but just kind of in the middle. Doesn't really have to be true middle. Well, it looks like the Chrysler symbol, doesn't it? Some of us may be too young to know Chrysler. That is the Chrysler symbol. But notice that I have 1, 2, 3, 4, 5 triangles. But what I'm concerned with is the interior angles, not the central angles. And that's what these are in the middle, are central angles, right? So we'd have, in this case, 5 times 180 minus the 360 degrees on the interior, right? You say, well, could we have done that up here? Yeah, I talked about the diagonal, drawing one diagonal. So what if we just kind of pick the middle and drew it like that, right? Look, we have 1, 2, 3, 4 triangles, and once again, that'd be 4 times 180, but one complete rotation there from the central angle, because each of those has that middle angle there, would be minus 360. Oh, look at that. That's interesting, isn't it? So here we had 180, one triangle, 180 degrees. Here we had 2 times 180, and here we have 3 times 180. Well, that's really interesting, isn't it? I think it's interesting. There's something going on here. Now, I'm going to leave it kind of you to investigate this a little bit further and see what else you can come up with, because there's definitely a pattern that we're already starting to see here emerge, and you can work this out. You can finish this up in either pathway. They're different formulas, and I think they're both equally powerful, and I think you should have both of them in your repertoire of understanding in terms to really grasp what's going on with these figures. And both of these have the really strong, powerful aspects to them. Like, this one's really straightforward and simple. This pattern might be something a lot of us see quite quickly and easily. This one has a different usefulness to us in that we might be a little bit easier when we start talking about area to think in terms of this instead of in terms of the diagonals. We're not doing the diagonals here. What we're doing is we're creating rays, if you will, from the central angle, and different ways of thinking about this. Spend some time, dig in on this, see what you can come up with. If you have questions or comments, just leave them in the comment section attached to this video, and I'll talk to you later. I'll be posting more on about this.